magnesia-bearing cements and their applications in soil remediation. So I'm going to stop sharing. Dr. Fee, it's all yours. Just see, yeah.
Yeah. Thanks very much, Professor Reddy, for your kind introduction. Really, it's a great honor for me to present my research in this platform, and it is myself is enjoying it very much so far, and I've really learned a lot from various topics that's covered in this seminar series. So, as I said, I mean, it's a great platform for students to learn new things, and also a great platform for the academics to exchange knowledge and to have very nice discussions after the seminars. Hopefully, I can have a few questions later, and then yeah, we can have nice discussions. So today, my topic would be on the topic that I have worked for the past few years. That is basically magnesia-bearing cements. And then today I'll focus on their applications in soil remediation. I think I'll probably just stop sharing my screen because I keep looking on the other side. So hope that is okay with all of you. So this is the topic of my the presentation today is magnesia-bearing cements and their application in soil remediation. So as Krishna just mentioned, I'm currently a lecturer at the Geoenvironmental Research Center, School of Engineering at Cardiff University. So a few slides to introduce our Geoenvironmental Research Center at Cardiff. We are a group of academics led by Dr. Devon Sapsford. And we are mainly working on geoenvironmental related problems. And then we have, in the labs of our GRC, we have state-of-the-art facilities for solid and liquid sample analysis and contaminant identification and quantification, including ICP-MS, ICP-OES, XRD, XRF, and also GCMS, etc. All of these, and also, as well as these solid materials preparation kits, including the polishing machines, ball mills, etc. That enables us to do a wide range of topics related to geoenvironmental issues. So in terms of the topics, as I said, we work on many of the problems related to the geoenvironment. We call it the interface between the atmosphere, hydrosphere, geosphere, and biosphere. And some conventional topics, including the fate and transport of the different contaminants in the environment, environmental risk assessment and modeling, and the remediation contaminant land. And in recent years, we are more focused on some emerging contaminants, such as microplastics, by Dr. Michael Harbottle, and we're more particularly interested in nutrient biogeochemistry as well, and resource recoveries from various kinds of wastes, and using low carbon sustainable routes. And also, again, I mean, carbon dioxide sequestration and storage in the ground or in construction materials are also one of our particular interests. So as I said, I mean, any students who are interested in doing geoenvironmental research are more than welcome to contact one of us if you want to have some ideas, or if you want to discuss some ideas to pursue further degrees or carry out some collaborations. So coming back to the topic today, I think that as the title indicates, I think that the magnesia cement is not very familiar to many of us because it's indeed a very special type of cement. It's actually a group of different cements incorporating magnesium oxide or magnesia. So today I'll start with something very basic from the Portland cement and its applications in soil remediation. That is mainly soil stabilization and solidification. And then I'll talk about why we are in a request to develop alternative cements or alternative binders for soil remediation. And then I'll talk about something more about how to get magnesia and what features they have, what characteristics they have. And then I'll discuss one by one the magnesia-bearing cements that I have worked in the past few years regarding their use in soil remediation. I'll also extract some of the literature studies to show you how versatile this type of cement can be in different applications. And finally, I'll conclude with some important findings, and also to provide some of my personal opinions, mainly on the challenges, opportunities for future research. And then if you are interested in the topics, related topics, you can look at some additional references at the end of this presentation. And of course, happy to discuss more after the presentation. So first of all, Portland cement. Okay, so Portland cement is the cement that we usually talk about. So because it's so widely used, almost 99% of the cement in the market is Portland cement. So basically, when we're talking about cement, we do mean Portland cement. So Portland cement, as we can see from these two figures, from the left figure, we can see that the production of Portland cement will continue to rise in the next few decades. That is mostly due to the more and more constructions and urbanizations in the developing world, while the developed world actually that they have almost plateaued. In order to produce Portland cement, in the raw materials, we need to have calcium carbonate. So basically from limestone. And that process actually decomposes calcite or limestone to calcium oxide and carbon dioxide. That forms a large part of the carbon dioxide emissions from the production of Portland cement. And that is chemically unavoidable because as long as you need Portland cement clinkers, definitely you emit that amount of carbon dioxide from the decomposition of calcite. Another large proportion of carbon dioxide emissions comes from the fuel and electricity emissions in the whole process. And so currently the two major routes of improving the sustainability of cement concrete industry. One is to improve the fuel and efficiency, or to use clean fuels like the biomass or bioenergy. Another route definitely is to tackle the process emissions that will need a very different chemistry, that we don't need to decompose these limestones to emit the carbon dioxide. But that one is more radical. Instead of just changing the fuels or improving the plant efficiencies. So today I'm talking about the second route is to tackle the process emissions, to use a totally different chemistry, of the materials to produce different kinds of cements. So to be fair, Portland cement, it's very well known for its good performance in different kinds of applications. First of all, of course, for construction materials. Second, for soil remediation, it also performs very well in most of the cases. And there are lots of the advantage of using Portland cement directly in soil remediation or soil stabilization and solidification. First of all, it is very cheap. It is widely available. The raw materials, limestone, clay, are widely distributed around the whole world. And then it has a very long track record of its performance as a construction material. And actually, the similar chemistry has been utilized almost 5,000 years ago by the Romans to produce cementitious materials. And Portland cement is also very effective to immobilize many heavy metals, including lead, nickel, manganese, etc. And is also compatible with many industrial byproducts, either as solidifying materials to treat these industrial hazardous materials, or just to incorporate them to improve the sustainability of the whole cementitious materials. On the other hand, there are lots of cons as well. As I just mentioned, the production of Portland cement is highly energy intensive and also carbon intensive. It is almost responsible for around 8% of anthropogenic carbon dioxide emissions. And also it is ineffective for many other metals such as chromium and arsenic. These exist mainly as oxide anions in soils and in the cementitious materials. So they are anions and not very well immobilized by Portland cement. And also some organics, most of the organics, and as well as zinc, will affect the hydration process of Portland cement very much. Therefore, if you have high concentrations of organics or zinc, the Portland cement hydration will be significantly retarded. And the last one, not the last one, but last but not least, the pore water pH of Portland cement is extremely high. That is because one of the main hydration products is calcium hydroxide. Equilibrium pH of that product is around 12.5, and plus other alkaline materials like alkalis like sodium and potassium. The pH water is usually above 13. That high pH will cause the redissolution of many heavy metals within soil. Later we'll see a graph of this. Apart from these pros and cons, in terms of long-term performance, the Portland cement is also has a lot of the uncertainties associated. We all know that the Portlandite or calcium hydroxide has very high solubility. So under the rainfall, they tend to be leached out. And also it is very it has a high tendency to be carbonated under the ambient carbonation conditions. So these will all degrade the Portland cement. And there are lots of other activities such as the seawater intrusion, the freeze-thaw wet-dry cycles, as well as the microbial activities. All of these are under-researched at the moment, and there's very little field data to support the satisfactory long-term performance of PC-based soil stabilization solidification. So that sets actually the background of why we're developing alternative cements. So first of all, the carbon dioxide emissions, we need to really treat it seriously to improve the sustainability of cementitious materials. Second of all, we need to, sometimes the Portland cement doesn't perform quite well in particular applications as a remediating reagent. So we need to develop something more specific and could perform much better in soil remediation some cases. So this figure shows us the current most developed alternative cements. This is according to the chemical compositions. So calcium sulfate aluminate cements, calcium aluminate cements. These are based on the similar chemistry, but using mainly the ettringite as the main hydration products. The gray boxes are alkaline activist cements. These are a very large group of different cements using aluminosilicate materials as the major raw materials. That has been claimed to have a much lower carbon dioxide emissions compared to Portland cement because it does not involve any decomposition of these carbonates. And however, the magnesium-bearing cements are not included at all because it is, again, it is totally based on a different chemistry. So this graph diagram cannot capture it according to the specified chemistry. So today I'm going to talk about the various kinds of magnesia-bearing cements and how they perform in soil remediation in particular. So this graph shows us the trend of the published articles, particularly for magnesia and magnesium oxide, for soil stabilization and solidification, as well as some industry byproducts like the slag or GGB and ground granulated blast furnace slag. So we can see an upward trend in the past few years, although the stabilization and solidification treatments in the US Simple Fund programs keeps declining over the years. And another trend I want to emphasize is actually the red one about using biochar for soil stabilization. I think Professor Reddy just gave a presentation this morning. Unfortunately, I was unable to attend it, but hopefully that was recorded so I can watch it later. But that actually gives us a very good implication that there are more and more attention to stabilization only instead of solidification, because soil is a natural asset. And if we're always solidifying the soils with any contaminant inside, we actually deprive the soil of its natural functions as a medium to grow things on top of it. So more and more, we are looking to stabilization. We want to decrease the bioavailability of these contaminants that can enhance the fertility or enhance the soil health in the end. So this is something that later I'll talk about when we are using reactive magnesia itself as a stabilization agent instead of a stabilization and solidification together. So we've talked about the magnesia, why we're developing these alternative magnesia-bearing cements. And now let's have a look at theoretically, how much can we get from this earth about this material. So these two figures shows you the theoretical abundance of different elements in the earth crust as well as in seawater. So these two major sources of elements on this earth. So if we want to really replace Portland cement, we definitely have to look at those elements that are abundant on the same order of magnitude. So we have to turn to these rock forming elements. That is why these alkaline activated cements are promising, because they are mainly based on aluminum and silicon. While magnesium element, you can see from the left figure that it's quite similar. The abundance is almost at the same order of magnitude compared to calcium, which is the main elements in Portland cement. On the right-hand side, you can see that the magnesium, the content in the seawater is almost 3 times higher than calcium. So theoretically, there's almost unlimited resources of magnesium that we can use on Earth. But in reality, this is a totally different story. If you look at these current resources for magnesium oxide or magnesia, the main natural resource we use to produce this material, commercially available magnesia, is magnesite. So it's a magnesium carbonate ore. That probably accounts for about 70% of the current commercial magnesia we can get. And we also have some of the magnesia from the seawater precipitation and then calcination. But that creates a big problem actually, because if we look at this figure, it shows the magnesite reserves worldwide. We can see that the magnesite ore is highly unevenly distributed around the world. Mainly China and Russia, these two countries almost hold all of the reserves in the world. That creates a big problem if we want to scale up the production of magnesia, because only these two countries has lots of this magnesite. All of the other countries will tend to these two countries to get this material. So this is definitely not good. But another alternative route is to use magnesium silicate ores. As we can see, if you still recall, the last slide is the abundance of magnesium. Most of the magnesium actually are contained in these magnesium-rich silicate ores. So this figure shows us the magnesium-rich rocks around the world. We can see that it's almost evenly distributed. It's almost everywhere. And it is very abundant in most of the countries. It's mainly contained in these silicates, serpentine, olivine, talc, and many others. We also have lots of the industrial byproducts or waste that we can extract magnesia, or we can utilize them directly. For example, some studies use the low-grade magnesia directly for soil remediation. And some studies use the salt lake, the magnesium chloride solutions to produce magnesia as well. These can produce very high purity magnesias. But again, I mean, there's still a lack of studies on using these industrial byproducts or wastes. So this table summarizes all of these chemical reactions that we can use these raw materials to get magnesium oxide. So as I said, the first one, magnesite ore, is the dominant source for the commercial magnesia. And then seawater brines are mainly used in Western countries, but it's very costly. But it produces a very high purity magnesia. And then the middle one, the magnesium silicate ores, this is the one I think is very promising, because chemically it is carbon neutral, because in the first place it absorbs the carbon dioxide to produce magnesite and then release carbon dioxide out. So chemically it is a carbon neutral process. But the problem at the moment is that the whole process of getting the magnesium silicate to carbonate is highly energy intensive. The reaction only happens at very high heat and pressure in order to increase the reaction rate to have the magnesite in the end. But it does have implications in geological storage of carbon dioxide. So the recent studies conducted in some Norwegian countries showed that if you inject the carbon dioxide underground at a certain depth, the reaction rate will be significantly higher than if you conduct it under the ambient temperatures. So that is probably one of the ways that we can think in the future can produce these very cheap magnesite, and also as a means of store carbon dioxide underground. But today, again, I'm going to focus on the mag side, on the magnesia calcined from magnetite ores. That is the commercial magnesia you can get at the moment. So most of us should not be concerned with this, how these magnesia are produced. But as an engineer or as a designer, we are more interested in how they perform or what the properties these materials are, so that we can design something using this material. Now that gives us this slide about the characteristics of magnesia. There's a conventional way of categorizing magnesia. That conventional way is based on the magnesia calcined from magnesite. So the first grade is called the light burn magnesia, or most of the cases I just call it reactive magnesia, because it is the most reactive magnesia we can get. The calcination temperature is below 1000 degrees Celsius, and it has the high surface area. It has been widely used in environmental applications like acid neutralization or as a dissolvent. And if you increase the temperature to 1400 degrees C, you get heartburn magnesia. This grade of magnesia is mainly exclusively used in China as an expensive additive to compensate the shrinkage of concrete in China. If you further increase the burning temperature, calcination temperature, then you decrease the crystalline size. As you can see from these figures, the crystalline size keeps increasing and the surface area keeps decreasing, and you have a much lower reactivity. Okay, so the key idea here in this slide is that if you increase the temperature, you get much lower reactivity. Much lower reactivity usually means that much lower dissolution rate, much lower reaction rate with other phases. So that is the conventional way of categorizing magnesia. And even within the reactive grade of magnesia, so those calcined at this lower temperatures, the characteristics or their reactivities vary vastly as well. So one of my task in my PhD is to categorize these reactive grade magnesia based on their different indicators. So this figure shows an arbitrary categorization of reactive grade magnesia based on their surface area as well as chemical reactivity. So I've categorized into three groups: the low reactivity, medium reactivity, and high reactivity. These are purely arbitrary, but it gives us like a rough guidance of which ones we are using. And the reaction rate with different phases is really depending on which phase you are going to react magnesia with. And then let's have a look at the hydration and carbonation characteristics of magnesia, because they are related to the magnesia-bearing cements. So if we just put these reactive magnesia in water, because they have very high specific surface area, so the dissolution rate is quite high, and it reacts with water readily to produce brucite or magnesium hydroxide. The magnesium hydroxide, compared to portlandite, the main hydration products of Portland cement, it has much lower solubility, almost 6 orders of magnitude lower. And in terms of the equilibrium pH, the commercial magnesia usually gives us an equilibrium pH between 9.5 to 11.5. If you look at this figure, you can see this metal hydroxide solubility graph. You can see that pH range is almost optimum for precipitating many of the heavy metals. But if you're using lime and PC, because of the supersaturated calcium hydroxide, you actually have much higher pore water pH, usually over 12.5. That will cause the redissolution of many of the heavy metals like lead and zinc and cadmium. So that it's sometimes will cause the problems of using PC for soil stabilization, solidification. And if you subject magnesia into the carbon dioxide, high concentration of carbon dioxide, you produce various kinds of hydrated magnesium carbonates. Theoretically, thermodynamic, the most thermodynamic stable phase is magnesite. It should go back to magnesite. But in reality, this reaction is kinetically hindered. So most of the cases, you won't get magnesite directly. You actually get nesconite or hydromagnesite or dipingite. So these different kinds of hydrated magnesium carbonates. So these hydrated magnesium carbonates, they develop very high strength. Later you see some of the images of these. These are either needles, flowers, or platelets with very small crystal size. So if you are using carbon dioxide, high concentrations of carbon dioxide under the ambient temperature with humidity, you are producing a very dense microstructure that gives you very high strength. And these figures actually shows the whole picture of the magnesia-bearing cements. The first two figures shows you the microstructures of magnesite and brucite, either from the magnesite or from the precipitation of the seawater. And then you can use different calcination temperatures in order to get magnesia samples with different reactivities, different surface areas. And then put the magnesia in water and to hydrate them, you get different morphologies of brucite and different particle sizes as well. And then if you carbonate these magnesia or brucite, you get different morphologies of different hydrated magnesium carbonate phases. And these are not the full picture because, as I said, because of the high reactivity of magnesia, reactive magnesia, they readily react with all sorts of different phases, such as the chlorides, sulfates, silicates, aluminates, and phosphates. So these are the basis for developing various kinds of magnesia-bearing cements. So today I'm going to only focus on a few of them that I have I'm more familiar with. And the first, only these highlighted ones I'll talk about today. For those magnesium-bearing expansive PC, magnesium MOC, MOS, and magnesium silica hydrate cements, if you're interested, you can explore further in the literature I give at the end. And today I'm going to talk about the carbonated magnesium cements, magnesium phosphate cement, and magnesium-bearing alkaline activist cement. So before going to these cementitious materials incorporating magnesia, I would like to first of all introduce some of the soil stabilization applications using reactive magnesia itself. Okay, so reactive magnesia, when it's in contact with water, it develops brucite. Okay, brucite is does not produce a lot of the binding. Using reactive magnesia at a certain dosage, you actually are only applying stabilization instead of solidification. So these data showing the high effectiveness of using reactive magnesia itself in remediating lead contaminated soils. So only after 1 day, the leaching concentration is below the regulatory levels. And these figures, after the letter M means the reactivity values. So the lower the values means the higher reactivity they have. So we can see that when we subject these treated soils to the durability test, we design a durability test to see how it performs over the years. So we can see that the durability are quite different depending on the reactivity of magnesia. This again raises the question that how are we going to use the cracked magnesia to do the soil stabilization? And one of the reasons we speculate is probably due to the highly reactive ones could probably be carbonated more easily in order to immobilize the heavy metals. But lots of the further studies are warranted. And this is another study that I extracted from the literature. This is a quite important one conducted from a Japanese group. So this study shows that using reactive magnesia as a soil stabilizer or soil amendment, it does not only just reduce the weak acid soluble cadmium, but if you are doing planting things on top of the soil, the wheat and the rice, you see that there's a very good reduction of these heavy metals within these edible parts of these plants. So the cadmium in the wheat grains are decreased, the yield of the rice increased significantly, and the cadmium concentration in the rice has decreased significantly after application of reactive magnesia. So that is a good example that we're using magnesia just as a soil amendment instead of solidifying the soils. And then go to the cementitious materials again. I mean, we can see that if we are using the carbonation technology, the enforced carbonation, using high concentrations of carbon dioxide to cure the magnesia-treated soils or contaminated soils, we see a significant strength increment after carbonation of only a few hours. So these figure shows that if you're looking at these solid points, you see that no matter how much how high concentration of the heavy metals are, the carbonation system always develop much higher strength than the Portland cement system. And as I said, if you look at these points, you see that Portland cement hydration is indeed significantly hindered by high concentrations of zinc. But magnesia, the carbonate magnesia system are much less affected. Similarly, if you have no solidification or cement hydration at all, the zinc leachability would be extremely high. While for carbonated systems, all of the leachability of these heavy metals are below the regulatory limits. So this actually provides a method that can be used to both store the carbon dioxide in the ground as well as immobilizing the heavy metals. But again, it is a solidification and stabilization combined method. And the next cement I'm going to talk about is called the magnesium phosphate cements. So this cement is based on the acid-base reaction between a magnesium oxide and a phosphate source. So in cement and concrete studies, people usually use dead burn magnesia. If you still recall what it means by dead burn magnesia, it is the magnesia that has been calcined at the highest temperature in order to give it a very low reactivity. That is because, I mean, if you look at these reactions, the acid-base reactions usually happen very fast, but it is highly exothermic, so it emits lots of heat. So you need to control the reaction rate in order to slowly release the heat to gain the strength. So this reaction rate is controlled by using the dead burn magnesia instead of the reactive grade. But later you see in soil remediations, actually you can change the grade of the magnesia in order to suit your needs. And also you can change the reactivities of the phosphate phases as well. And later you see some examples. But basically these magnesium phosphate cements are quite versatile. They can be used for rapid repairs. If you look at the compressive strengths, even using the dead burn magnesia, the compressive strengths can be as high as 35 megapascal in only 3 hours. So that is this cement is mainly used for rapid repairs and some very special applications. But today, of course, the topics on soil remediation. So I'll just pick some examples of using the modified MPC for soil remediation. So this graph is extracted from one of the Antarctic study of using modified MPC for contaminant soil remediation. Because it's an Antarctic soil, so the temperature can be as low as minus 20 degrees C. So under that extremely low temperatures, the normal cementitious materials doesn't work, because most of the cementitious materials, particularly Portland cement, it needs a temperature. It only reacts at a certain rate at ambient temperatures or higher temperature, because the reaction is exothermic. It needs, if the temperature is extremely low, the hydration will stop. But because MPC is based on acid-base reactions, it is less affected by the low temperature. So in this study, actually the reactive grade of magnesia is used with sodium phosphate solutions. And as we can see that this cement treated the soil quite successfully at decreasing the solubility of the leachability of almost all of the heavy metals in this Antarctic soil. Another modified MPC system is actually one of the studies that I've conducted in collaboration, mostly conducted by Professor Du from Southeastern University and Professor in collaboration with Professor Reddy as well. So this is a modified MPC based on phosphate rock, acid-treated phosphate rock, as well as reactive magnesia. So this one, as I said, it is using the acid-treated phosphate rock in order to control the release rate of the phosphate to control the reaction rate. So using reactive magnesia, we can get the stabilization of solidification very quickly. And then the slow releasing magnesia, the phosphate ions from the rocks contribute to the long-term effectiveness of the. So that works quite well for heavy metals like lead. And the last one I would like to introduce is Magnesia-bearing alkaline active cement. So that is based on the Magnesia and GGBS. GGBS is a byproduct from the iron making industry. So the composition is quite complex. It is a glassy structure, mainly composed of calcium oxide, magnesium oxide, alumina, and silica. So if you subject to XRD, it is an amorphous hump. It's a very broad hump. There's no crystal structure of this. But if you mix it with magnesia, the hydration of magnesia creates an alkaline environment that will attack the slag particles to release all of these monomers, polymers, and then they will rearrange and then precipitate or crystallize into various kinds of reaction products. These include these common cementitious products like CSH, calcium silicate hydrate, magnesium silicate hydrate, as well as the last one is called the calcium aluminate hydrate or magnesium aluminate hydrate. This is commonly called layered double hydroxide, we call it LDH. So this is a very interesting phase I found in this type of cement, and it has lots of the implications for soil remediation. So from the X-ray diffraction, we can see a very clear peak of this phase. And this gives us a crystal structure of this LDH. It is actually a layered structure. And another name of this clay mineral, is called anion exchange clay. Why it is called anion exchange clay is that in the crystal structure, the divalent ions are substituted by the trivalent ions, and then the surface are positively charged. So in between, in the interlayers are filled with the anions. And these anions can be exchanged. So that is why it is called anion exchange clay mineral. And all of these divalent and trivalent ions can be substituted by others. So that is that has been demonstrated in one of the studies of mine of using Magnesia-GGBS cement to treat the high concentration of zinc and lead. If you look at the X-ray diffraction for high zinc sample, you can see the shift of the despacing, indicating the incorporation of zinc into the crystal structure of this hydrotelside or LDH. And also another benefit is that this LDH is, has a high pH buffering capacity. So after the TCAP leaching, you can see that the pH is buffered at around 9 to 10, which again is almost the optimum pH for precipitating various heavy metals. And of course, the laboratory study doesn't tell us most of the things, not all of the things. So we've also conducted field trials comparing this Magnesia-GGBS cement with Portland cement. So here I'm going to introduce a little bit more on the Project SMART. So this is the largest research and development land remediation project in the UK. And a field trial was conducted in the UK in 2011. And after 3 years, I went to the site to retrieve some of the soil cores, in particular this stabilization solidification cores, and to do some further analysis about the effectiveness of the SS treatment under the field conditions. So a few important findings were reviewed from the lab analysis. So first of all, the magnesia alone can provide negligible strength. As we just mentioned, there's almost no solidification, but it significantly improved the immobilization capacities of both organic and inorganic contaminants, as we can see from these circles. The metal leachability are the lowest among all of these binders. But if you do need the solidification, you need strength to your treated soil, then you just simply replace magnesia with this industrial byproduct, GGBS. You can include almost 90% of it. That increases the strength significantly. As we can see from these circles, it is even much higher than Portland cement. And the permeability are on the same order of magnitude. And more importantly, the metals and leachability are significantly reduced, almost 1 order of magnitude than the PC-based treatment. And then the pH values stayed around 10.5 to 11. Which is definitely much better than the PC ones. If we compare the time-dependent performance within these 3 years, we did actually 3 data points after the installation and after 1.5 years, and then the final 3-year data. So we see that in this very complex field soils, it is contaminated by various heavy metals and lots of the PAH and total petroleum hydrocarbons as well. It's very complex, but we see that using magnesia and GGBS blends, it develops much higher strengths, both in the short term and in the long term. That demonstrates the good compatibility of this cement with these complex contaminants. And in terms of the pH values, as I just mentioned before, although the Portland cement gives a very high initial pH of around 12.5, over the years under carbonation and rainfall infiltration, the pH values decrease significantly to below 10. And on the other hand, although magnesia GGBS cement has a lower initial pH values, but in the end it stabilized almost at 11. So that is very good for soil stabilization, solidification. And in the end, of course, I mean, because of the better pH buffering capacity and high strength, low permeability, in the end, the magnesia GGBS cement performed much better in terms of immobilizing the total metals and total organics. So yeah, in the end, a few conclusions, and hopefully it's still within the time limit. And a few conclusions. First of all, magnesia-bearing cements could be produced via various pathways, utilizing abundant natural materials and waste resources. But these require a lot more research efforts. The reactivity of the magnesia samples varies significantly depending on the sources and production methods, as we just saw. And on the one hand, it allows for fine-tuning of its characteristics to produce these tailor-made remediation materials, really depending on the applications you want to use them. But on the other hand, it actually could lead to a lot of the forced use or the failure of the applications if you haven't developed a very good understanding about this material. And the invaluable field trials demonstrate that these cements do outperform PC in both the physical properties, contaminant immobilization in 3 years under the field conditions, which hopefully will help the development of the full-scale non-remediation strategies. And in this smoke project, we actually tried various technologies, like not just soil SS, but also permeable reactive walls, the low permeability cut-off walls using these magnesia-bearing cements, but the results are not reported here. And it's very crucial to develop more sustainable remediation materials for soil remediation with better durability and lower carbon footprint. But more efforts, from my opinion, should be devoted to regain or enhance the soil facility and soil health, and also to investigate more about the soil-plant interactions instead of just totally deprive soil of its plant growing capacity. So although we have known quite a lot of these magnesia-bearing cementitious materials, particularly in construction materials, but there are still a lot of challenges, and also these are the opportunities for us to look further or research more around this topic. I'll just list a few of my thoughts, but definitely there should be many more. So first of all, we can explore more sustainable sources of magnesia-bearing cements using abundant silicate materials or brines, etc. We can combine mineral carbonation and soil remediation technologies. Actually, there are some efforts already to use this magnesium silicate to spread onto the agricultural soils to sequester carbon dioxide and also remediate soils. We need to look at mechanisms in more detail about the interaction between novel cements and the contaminants. That gives us a better idea of how they perform in the long term. And find the last one is probably something that I could probably more interested in, is to use these magnesia-bearing slow-releasing fertilizers like the layer double hydroxide to enhance the fertilizing efficiency or to enhance the soil health. So, and as I said, there are many more, but all of these topics will call for interdisciplinary research, including soil science, materials engineering, agricultural science, environmental engineering, and many more, biological science, etc. So it is a very complex topic, but I mean, it really depends on which direction you are more interested in, and then there are lots of opportunities for us to work. So in the end, I would like to thank all of these, my supervisors, professors that guided me to study all of these topics, in particular, Professor Altabar from Cambridge, Professor Du from Southeast University, and lots of my former colleagues. And also thanks our survey for publishing our first book on magnesia cements. So if any of you are interested in this topic, you can look for these additional references. And definitely, if you have any questions after the seminar, please feel free to ask, and also hopefully we can have a nice discussion later on. So that's all of my presentation. Thanks very much.
Very good.